So thank you. Good afternoon, everyone. Today I want to present to you the latest development of our kite simulation tools and the experiments that we have run to try and validate it. First, a brief introduction on our simulation tools and a description of our current experimental setup, and then we will jump to the results. So we are using LAXA. LAXA is a series of simulation modules based on MATLAB, publicly available on GitHub. Over the years, other modules have been developed. The first three, Kite Acrobat, Kite Flex, and Kite Surf, were based on a minimal coordinate Lagrangian formulation, while the last two, Kite Terrain and Kite Elastic, are based on a elastic mechanics formulation. This last module, Kite Elastic, is the one that we are adapting to our current experimental setup, which is using a rigid frame delta kite with 3 lines. For the aerodynamic model of this kite, we are using the Unsteady Panel Method that Ivan has developed. We use this method to create a database of aerodynamic coefficients for the forces. And for the torques, we are using coefficients from the experiments that we ran in 2021. What we have added to Kite Elastic is, Kite Elastic, first of all, is a 6 degrees of freedom rigid body simulator. It's using a spring mass model for the tether. Basically, we have added a closed loop controller based on a simple PID based on the work of Uwe Fresner. And also we have coupled the new aerodynamics of the kite. So this is the experimental setup that we are using. If you were in my presentation in the Airborne Energy Conference, you may remember this picture. Since then we have made a few changes. The most important one is the addition of losses directly attached to the anchoring points of the line to the kite. The reasoning behind this is that before we were measuring the line tension with these mechanisms on the ground, the running line tension meters, which are measuring the line tension indirectly, since the tether has to freely move through the mechanism. But that indirect measure, we weren't completely sure of it, so we wanted a direct measure of the tension. Besides that, we have a differential GPS system, and all of this information is going to the ground through a 2.4 GHz data link. And together with the data from a ultrasonic anemometer, obviously all the actuators here, this is going to a real-time controller, and that goes to a workstation just for logging purposes. This is the flight test that we did a month ago in Santa Maria de Mera, which is I think it's the village with the highest altitude in Madrid. This is our kite, actually. I don't know if you can see here in the picture, but here you can see the shape that I think Ivan had a question earlier, that is not completely flat. Here you can see the fault. That's the machine mounted on a track that we recently acquired. And yeah, this is being controlled right now on open loop, so just using a joystick. Here we are trying to achieve some nice figures of 8. Trying. So this is the nicest series of figures of 8 that we had, 3.5 basically. In the top right corner, you can see the reconstruction of the flight path. Down, you can see the input that we were putting into the kite. So line delta of 10 centimeters, more or less, alternating between plus and minus for the tanks. If we look at the tensions, we see that the central line is the one with the higher tension, around 400 newtons, and then we have the control lines alternating. So here the green one is the red one, and so you have first and to the right, the right line has a higher tension as one would expect. Basically around 300 newtons, and then the other control line goes 150. This whole trajectory, 3.5 figures of 8, took around 17, 18 seconds. If we look at the peaks of the tension, they are more or less at the end of the, let's say, straight part of the figure of 8, just before the turn. And then the lowest tension is basically when the kite is losing a lot of velocity at the end of the turn. If we compare that to the results of the simulation, so first, here we can see the controller in action. We have limited the delta line that we are using to match the experiment, so maximum 10 centimeters. Obviously, in the middle, this is the PID controller working, so it's not the same as the manual inputs, and the trajectory is similar, but not exactly the same. If we look at the tensions, the first thing we can see is that the center line is not the one with the highest tension anymore. If we add all the three tensions, they match with the experiments, but the distribution is not the same. We are not still yet to understand why is that, but we think it may be a combination of imprecisions in the parameters of the simulation and also some aerodynamic aerodynamic effects. Besides that, we get this alternating pattern. The line tension is now a little bit higher on the control lines, around 350. The peaks and lows are, again, more or less at the end of the straight line, at the beginning of the curve, and then a little bit earlier, but at the end of the turn. One interesting thing that we noticed was that comparing the tension measure on the losses on the air and the tension meters on the ground, for the control lines we see a better definition of the tension with the direct measurement of it, especially when there is a few little load on the line, because the friction of the mechanism prevents it from moving. But we're also surprised to see that in the central line we seem to have some kind of mechanical issue, because the measurement on the ground is very much dampened with respect of the true measurement. We are yet to study this, but this is also true that this tensiometer is using a much heavier duty load cell than the other one, so that may explain it. So yeah, in conclusion, we have adapted our simulator to our current experimental setup, but we still have to make some adjustments. But the new load cells are giving us better measurements of the line tension, and for the future we want to put the multi-hole pitot tube on the kite to better understand to measure the angle of attack in situ and better understand the disagreements. We want to fully integrate Unpad into LAXA, so we run the unsteady simulation in parallel to the dynamic simulation. And then finally we want to leverage all of this framework to develop a closed loop controller and actually try it on the real kite. So thank you very much. If you have any questions, I'm looking forward to it.
Thank you, Francisco. A question for myself: is this measurement data available? Because we currently have a large EU project, Meridional, where we combine all globally available data from airborne wind energy systems into one large data hub.
Right now it's not available because we just did it last month, but we want to first publish this code on GitHub also, and also we can make it publicly available, the experimental data, so yeah, that would be
would be very valuable, maybe as part of the presentation, to then also make the data accessible. Thank you. Are there any questions? No, then thank you again, Francisco.